So we already know how to do number one, right? This is just plugging in the integral form of the differential equation. Now we are going to look at what are the alternative ways of performing flux reconstruction. How do we approximate the flux using the cell averaged values? The most straightforward way of reconstructing the flux, let's look at a particular interface, I plus half, and I have a cell average I here and a cell average I plus 1 here. And remember, we don't have the value of the function. We only know the cell averages, right? Okay, so the simplest way to do it is let's just do Taylor series expansion again, right? So let's do Taylor series expansion again. And let's do Taylor series expansion upon this I plus half point. So, for example, I know my u is going to be u at I plus half. Okay, plus a delta x. My u at any x I plus half plus delta x is equal to this times partial u partial x plus half delta x squared, delta plus etc. Right? So from this, I can compute my volume averages. I know my ui is going to be 1 minus 1 over delta xi times integration of delta x goes from 0 to delta xi of u x I plus half plus delta x and d delta x, right? Does it make sense? I'm integrating u over a delta x. Delta x would be equal to 0 here, and delta x would be equal to delta x. Oh, ui should be integrating over minus. So here is delta x equal to delta x I plus 1. Here is delta x equal to minus of delta xi, right? So this is what I should be integrating, and I think I should change the order so that I'm actually integrating from minus delta xi to 0, and the u of I plus 1 would be equal to 1 over delta xi plus 1 integration from 0 to delta xi plus 1 of the same quantity. Right? So this Taylor series analysis is going to be integrated over a domain, yes? Because I'm defining the delta x to be 0 here, and I'm defining delta x to be x minus xi plus half. Right? I'm defining delta x to be whatever x I have in the domain minus the x at the interface point, so that it's easy to expand my Taylor series analysis at this point.
Can you write the definition?
Sure. So delta x is going to be my x minus xi plus half. So this is basically ux, right? Okay, or yeah, okay. Or x is equal to xi plus half plus delta x. So if I plug in the Taylor series analysis, this term is a constant term. So integration of this term is just going to give me delta xi times the constant. So here what I'm going to get is u of I plus half, right? This is contribution from this term. Contribution from the second term is a linear integral, right? And the linear integral is going to give me half of delta xi. Oh, I think it's minus from this point. Half of delta xi divided by delta xi times sorry, delta xi half of, so this is linear integrated would be square, so I get a square delta xi times partial u partial x. So this is from the linear term, right? I'm just integrating this linear function over a domain from minus delta xi to 0. All right. Okay, and the quadratic term is integrated into a cubic. So what I would get is over 6, because I already have an over 2 here, and the integration is going to get me another factor of 3, and I'm also dividing by delta xi here, plus etc. Integrating over the right hand side is going to give me similar things. So the first term is ui plus half, the second term is going to be plus delta x I square I plus 1 square over 2 delta x I plus 1 du dx, right? And plus also quadratic terms and cubic terms, right? So if we use this Taylor series expansion, which gives me approximation, if we truncate the Taylor series, it gives me an approximation of the cell average values expressed as a function of the interface values. Then I can figure out a way to perform a linear combination a times ui plus b times ui plus 1, then would be as accurate approximation to ui plus half as possible, right? So in order for me to do that, if I want a times this plus b times this to be exactly equal to 1, right? So a plus b has to be equal to 1. And I also want this and this to be equal to 0, right? To cancel as many terms as possible. So I have a times delta xi minus plus b times delta xi plus 1 is going to be equal to 0. And then the quadratic term we have no way to cancel, right? So if we just solve these two equations to get what should be the multiplier on the ui and ui plus 1, what we get is, for example, for the simplest case, if delta xi is equal to delta xi plus 1, we get a equal to b equal to half. It's just a simple average. The interface u should just be an average between the volume average on the left and volume average on the right, right? That's just from Taylor series approximation. And if the two delta x's are not equal, then the weight is going to be a little bit different. So a should be delta xi plus 1 over delta xi plus delta xi plus 1. B would be equal to delta xi divided by delta xi plus delta xi plus 1. So it's a weighted average where the weights is proportional to the size of the other volume, right? If I have a smaller weight, if I have a smaller width, then I'm going to be weighted higher because the center of the volume is actually closer to the interface. So if we use this scheme, we are going to be approximating my f at I plus half using, there are two different approaches, using either the what I'm doing here, which is taking f, the function f, evaluated on AUI plus a weighted average of UI and UI plus 1, right? Or you can do a similar analysis to f, and what you get is u of a times f of UI plus b times f of UI plus 1. All right. So the analysis is going to be the pretty much the same. You get a different quadratic term, but the linear term is going to be the same. So this is, according to Taylor series analysis, the most accurate scheme I can use to approximate the flux at the cell interfaces.